I think an official this semester that actually got applause beforehand.
Sweet.
We'll see if you get it at
Good sign.
I don't think that's screen sharing.
Oh. Here. Let's see it now. We're ready. So, hey everyone. I'm gonna talk about my time at Livermore National Lab. So the way I kind of wanted to structure this talk, because I've given this talk like 7 times already for job interviews and stuff. I kind of wanted to talk about this one, like kind of introducing Livermore Lab, what it's kind of like to work in that environment, and like the potential for careers there. It's a pretty elusive job to get, but I'm going to talk about it anyway, and you're going to have to listen. So,
Well, and the fact that you've already gotten 7 interviews probably makes it worth listening.
yeah.
Right? That's a good thing.
So we're going to be improving remap software via low order refinements. I was a part of the weapons and complex integration division under my mentor Arturo Vargas. And then I've got this long list of people: Veslin, Vladimir, Will Pasner, Sanyo. These guys are all brilliant. They're part of the MFEM development team, which we'll get to look at it later. So just to break this up, we're gonna just to introduce things. To introduce what's going on, we're going to talk about the infrastructure of FM and repos, which are the 2 coding software that I mainly worked in. And then we're going to talk about mass-based element average solution for finite element. Then we're going to get into my main contribution, which was the low order reduced mass-based element average, where we're going to talk about kind of mainly like what I did, what the process was, how we did some problem solving, stuff like that. And then we're going to talk about projecting from a refined mesh to a not so refined mesh. And then we'll do everyone's favorite part, numerical results. We'll get pretty pictures. So Livermore National Lab, right? So this is in the Bay Area, in particular, Livermore, California. You can kind of see it right up in there. It is about as far away as the Bay as you can get, which means you get the worst weather at the Bay. This is about a square mile. Some people call it the smartest square mile on Earth, but considering some of the conversations me and my office mate had, probably wasn't the smartest at the time. I think we were about right here. This is where we were stationed at. We were in something called the cooler, which was where interns and new hires would go if they didn't have their Q clearance. Just some background on what the lab is known for, what it does. They're co-creators or co-founders of various types of elements. If you see element 116, that is Livermorium, named after the lab. They took a big role in help creating and developing these new post-transitional elements. Other stuff that they've done, you can kind of see. Does anybody know what this is right here? Is that a nuke? It is a nuke. So Livermore LLNL was founded in the 50s, right after nuclear bombs started to really take off. And that's kind of what their main drive for researching was. So we had a talk where it was just some guy going into the physics of the first couple of nanoseconds of what a nuclear detonation looks like. It was really fascinating. Then this right here, this actually is pretty recent. Everything over here. Does anybody know what's going on there? Somebody should know. So it's September 26th. NASA launched a satellite and a meteor that changed the trajectory. People at Livermore were behind some of this, and they were spearheading the Planetary Defense Group, which is an amazing name. And then, in my opinion, the most interesting thing is that it's kind of hard to see. There's kind of a lot going on here, but this is a part of something called the National Ignition Facility. So if you're familiar with what ignition means, it means burning plasma, which is nuclear fusion. So NIF, National Ignition Facility, kind of can't see because of the zoom thing. I'll put it. Yeah, I can't really do anything with that. It's kind of
hide it more. And then hide floating meeting post.
See that? Here it is. Anyway, so what NIF really is that it is a giant building that was developed in the last, I don't know, 20, 30 years. It was in the 90s, 1991 is when I think they started. And it's a giant sphere, which is what's in here. And what they do is they have these long tubes, and these tubes are crazy long. There's miles and miles of these tubes where they just blast lasers all into one tiny little object. What happens here is they blast all of these lasers into two little bits in a cylinder, and it's supposed to start nuclear fusion, or that's what they're trying to do. And to achieve this ignition, you kind of need the fusion yield, the megajoules here. You need this to be about 1.6. In August of 2021, they got it to about 1.4, which is very, very, very close. However, it kind of is not really realistic to get there. Everything that happened there, like the experiments were absolutely perfect. It's not very reproducible, but it's progress, right? So that's just some background. You know, if that's some like material that you're interested in, then 100% maybe try to go down this career path. This is not what I did though. What I did in comparison might be a little bit more bland, but it's computation, so I think it's interesting. So at Livermore, we have something called Marbl. So this is a big hydrocode multiphysics package, right? So this does things like magnetism, high explosives, laser-driven experiments, so like exactly what we saw with NIP. So that's like a big overarching code. Below that, there's blast. So this is a high order finite element subcode. And this does various PDE solves. I'm not 100% sure. I never got the opportunity to use it. It requires more clearance to do that. But particularly, it requires 3 phases of computations. So the Lagrangian phase, where if you've taken, I don't think anyone in here has taken it, but if you're familiar with Lagrangian solves, then you're solving PDEs on a moving mesh, right? So you can kind of see the mesh is warping here. The mesh is warping with the solution, right? There's the mesh optimization phase that kind of happens in the middle, where you do some fancy stuff to make the mesh not so bad. And the remap phase is what we're going to be focusing on. This is where we take the solution and we make the mesh, we bring the mesh back to its original state. But we need to keep the solution. We need to keep the solution looking clean. So this particular phase requires solving the advection equation, which is right down here, right? So for if you've got a scalar field C and then a vector field U, or sorry, other way around. That's the equation we're trying to solve, which isn't a very difficult PDE to solve, numerically speaking. But what we want to do is we want to find methods to solve this that's bounds preserving, which means every new solution is kept between a bound of the previous solutions, right? So the new solution is never violating previous bounds. Conservative, which pretty much just means take the integral of the solution, take the time derivative, hopefully that's equal to 0. In general, this is usually true, especially in just in theory, right? Mass conservation, momentum conservation, that's the thing. Okay, and another subcode, but this is kind of the main structure that I was working with. So it's finite element code, blast, L3E, CEED, visit, stuff like that. Fully open source, anyone can download it and look at it if you want. Not gonna make it. Fully parallelized, comes with several example tests. If anyone's familiar with Deal 2, which I can probably count maybe 2 people in here might only be familiar with it. So yeah, then there's remhost, proxy at for blast. So it kind of replicates some of what blast does. Mainly focuses on solving the advection and remapping. And it is highly dependent on it. Again, fully open source. The code that's in there is somewhat translated into blast for bigger actual big web problems. And you can even look at my GitHub branch if you want. So what does remhost do? 2 tests, right? One of them is transporting, right? So that's just saying I've got these solutions here, and I want to shift them up through the mesh. Not very crazy. Anyone that's familiar with numerically solving numerical solves should know that this isn't a very complicated task. But then there's remap, right? With remap, we're twisting and warping the meshes, right? That's complicated, right? the point of finite element method is to get, at the end of it, is to get a matrix, is to get a linear system based on the elements. But here the elements are changing it. The elements are time dependent, right? So every single time step, matrix is changing. Things are evolving. It's not what we want. Causes more mass loss, right? So that's kind of what we're trying to do. We're trying to come up with a solution that does remap, but we're not getting mass loss. Okay. Now, for job interviews, people really like, especially when you're doing a computations job, people really want to know that you can do some coding. So a lot of this is going to be kind of computer sciencey. So again, goal is to solve advection. There's 3 methods. High order, the standard solve that anyone would have. The actual solves aren't terribly important, except for in low order, right? Low order depends on high order. And in general, high order doesn't preserve bounds, which is interesting that it doesn't do that, but it's, that's the hand that we're given. With low order, we're taking the high order method and we're kind of changing it so we get bounds preservation. And what we're going to be focusing on here is the mass-based element average. Okay, and then later we'll talk about this. It's FCT or flux corrected transport methods. These are kind of introduced. We're kind of taking the high order method, the low order method, kind of mashing, right? We have accuracy with the high order solution. We have nice properties with the low order solution. Mash them, make them a much better solution in general. Okay, so like I said, mass-based element average, this is what we want, this is what we're trying to do, or this is what we're trying to base our project off of. So here's kind of like a basic overview of this. So when we solve for advection here, right, we've got our, it's a little bit hard to see there, but you can kind of see this is on a mesh, right? Every single one of these cells, what I'm going to do is I'm going to find the average of the solution, and I'm going to set a new solution equal to that average. So instead of being, curved and nice and pretty, we kind of have this flat, nonsensical thing. Right? So this is very bounds preserving, right? And I think that's quite obvious because an average is always going to be bounds preserving. But this is highly inaccurate, right? This looks like crap. So what are we going to do? It's actually pretty simple. We're going to refine the mesh once, or however many times you want. That's the basic, that's the starting point. So the rest of this is going to be me talking about MFEM and kind of the nuances involved with programming in this setting, right? That was probably the hardest part of the internship, was trying to make my brain connect with MFEM. So these little arrows here, these represent element order, right? Whenever you're working with a finite element mesh, we have, and whenever you're doing a loop iteration for elements, they're going to follow a certain pattern, right? So normally, it's kind of this Z pattern where we're going bottom left, bottom right, top left, top right, etc. And whenever we do certain refinements, we hope to maintain this ordering, right? Now, MFEM doesn't treat all refinements the same, which is frustrating, right? So if I wanted to do, let's say I want to do make refine, right? This is what we want, right? This takes this backward Z pattern, and then on each of these sub elements, we have another backward Z pattern, and it's kind of a nice seamless transition of the same pattern that we want. But if I were to do the uniform refinement command, we get this like weird backward C thing, right? It's not what we want. So this was something that we struggled with for a long time. Well, long time, about a week. We didn't understand why things weren't working well, and it was because we weren't refining things correctly. And this lack of consistency is going to be important for the numerical integration right now, which we won't get super into, but that's where it's effective. So another problem, mesh order, right? Standard finite element mesh, right? We've got boxes, but sometimes, right, we're warping our mesh, right? So our meshes aren't constant or linear, right? They're going to be wavy. So if I define, my mesh order to be cubic, right? I expect to have some curvature there. So when I define our, we have our basic high order mesh here, this nice wavy looking block. What we expect to see by the end of it is just a more refined, wavy looking block pattern. But the way it was, is it just kind of interpolated it. Right, this doesn't look very good. The mesh order wasn't transitioning well into making a new mesh. So how did we go about this? We asked people that were smarter than us. Will Pasner, really brilliant guy. He was one of the guys that created MFM back in the day. He's now at Argonne National Lab, unfortunately, but talked to him for 15 minutes and he was like, oh yeah, I'm pretty sure it's just these 3 lines of code. So I won't get into the details here just because that's a whole thing. But whenever you're programming, sometimes it is just a couple lines, right? And I don't know. A lot of that's why I kind of like working with teams. It's kind of nice you have people that you can talk to. We had a Slack channel where I would just post all of my dumb intern questions. So we refined the mesh. Everything's looking good. We have this coarse looking block, now we have a finer block. And it's a pretty simple solution, right? Like we're just going from this big guy to this even more refined, bigger guy, right? This looks a lot better than the first one, the first mass average solution. And all it is these 7 lines right here. So this is step 2, relatively easy. Nothing much is happening. But oh my God, let me tell you, step 3 was the worst. So we can't just, whenever we have a mesh, we bring it in, we expect the solution to have that same mesh, right? So we can't just output this refined mesh. We need to map it back to the original mesh. That's what we need to do. This was a nightmare. This took me a very long time to figure out. I think it took probably 3 weeks to a month. So what we need to say, hey, we need to, I mean, it's exactly what I said. We're just mapping from one to another. No, we're doing finite element, right? This might be a little bit hard for those that don't know finite element. I can only see a handful of people who may be actually knowledgeable in it. But I'm just going to keep talking anyway. So whenever we do the linear solve for finite element method, we are working with this type of integral right here. So we're taking u, we're multiplying it by something called a basis element. So a basis function or basis element, finite element is just kind of a very simple, like the most simple polynomial degree function. Whatever we do, it's hard to explain when you don't know it. Just take my word for it. Anyway, so
the PIs are like bases of some space.
yes.
So you're really just taking an inner product there, right?
Yeah, exactly. So we have this basic high order element, which is just this block with these degrees of freedom right here. But whenever we do a refinement, we have these sub elements. So omega 1, omega 2, and I say, hey, this integral right here over our basis element, our mesh element omega. Whenever I refine that, that's just the same as making the sum of the integral on these little guys, right? Same thing. But here's the problem. This basis element is the basis element for omega. And so is this one. So we're integrating over the sub elements, but we're still using the basis element of the big guy, right? That is a problem. Why? Because MFM is super object oriented, right? So if I define a finite element space, if I define omega, that already tells me what all of the basis elements are, right? So when I'm integrating this, and I say make this finite element space, this already tells me what the basis elements are, right? So if I'm defining it from 0 to 1, it says, hey, I know your basis elements are these spies. But whenever I do a refinement, and it creates more basis elements, but these aren't the ones that we want, right? These are smaller basis elements first. So what's going on here? Like, it's a little bit hard to understand, right? Because especially if you're not too familiar with finite element method. But here's what MFM thinks, right? Here's our high order element on the left here, and then here's the subscripts are disappearing on this, and I don't know why. Imagine this as omega 1, omega 2. You can kind of see what you're anyway. MFM thinks we are working with 0 to 1, 0 to 1. right? That's not true. It should be 0 to 0.5, 0.5 to 1. What we need to do is we need to trick MFEM into thinking that over this entire element, 0 to 1, right? That's what we need to do, right? It's not that easy. Well, it's easy, but it requires a little bit of caretaking, right? If you remember like any Calc 3 or linear algebra, you would know that we can do this with just a simple matrix multiplication, right? So if I'm trying to go from this big element here to this small sub-element omega 2, all it is just a matrix multiplication on every single element here. And then same thing with 3D, right? And the nice part about this is that we want to have a finer submesh, right? If I don't want a 2 by 2, if I want a 3 by 3, then we can just edit the values over here. I know I didn't remember this whenever I originally was doing this project, but you definitely learned it in Calc 3. I had to bring out some what was it, Paul's Calc 3 notes or whatever. But yeah, so there's a lot that's not being carried over here. I apologize for that. I don't know why it's not appearing. Anyway, with that, we do some numerical integration magic. We do some numerical integration magic. We do some linear algebra magic. We eventually get our mapping from the finer mesh to the coarser mesh, right? So this whole process, we go from the smooth guy to the finer but constant guy, and then we map him to the better guy, the one that's preserving balance, the one that looks good. Okay, so from a computer science standpoint, how does this look, right? So the basic LO solver right here, this is pretty much the class that determines the low order solves, right? So if you notice, we've got mass base average right here. That was the first one, that was that class, and then here's the new class that we created. Most of these classes have about 2, 3 max functions. We had to have 6 in here. So we have FCT project, which is the function that we use to map the fine element to the fine mesh to the coarse mesh. Node shift, that was matrix multiplication. Calc LO solution, this was the main polymorphism, and LO solver. If you're looking for a job in computations, 100% know that word, because I got asked what this word is probably about 3 times. Do you know what polymorphisms are? Do you know what class inheritance is? So 100%, if you're looking for a computation job, know that. And then the rest of these, calc LOR solution, that calc LOR refined solution, calc LOR projection, that again, that's part of the mapping process. So technical stuff that might be a little bit hard for some people to understand if they're not really computations heavy. Here's some pretty pictures, right? So this first column, we have the mass average. So that was whenever we're not doing any refinements. We included the plots and the log plots. Because in my opinion, the plots are not very telling of the situation, but the log plots really are. So here, we've got mass average. Let me go back.
This? What did you use to plot this?
So this was another software that the nerds at LONL developed. I think it was called GLViz. It's only for repos and MFEM. You can try to download it if you're good at Linux. Anyway, so we're doing this project problem right here, where we're just warping the mesh, right? So we expect to see this clean circle with the bar in it. We expect to see other clean circles down there. That's what we want to see. And when we're back here, with mass average, we don't see that. It looks like garbage, right? It looks like it's just smearing everything everywhere. That's not what we want to see. The log plot, I don't even need to explain. That looks like crap. Whenever we do LOR refinements, right? This looks better, looks a little bit cleaner, right? It's not super bright, it's not like a flashbang. And then the log plot, that looks a little bit better. There's still some smearage going on. But one thing to notice is that our mass loss is better, right? We want things to be mass conservative. We want this number to be as close to 0 as possible, right? So here we have mass loss on a scale of 10 to the negative 5. Here it's close to 10 to the negative 6. It's not that much better, but it's a little bit better. And then when we add 2 refinements, it looks even cleaner, right? There's not as much smearing. And especially in the log plot, we can kind of tell there's not so much red everywhere, right? And then with 3 refinements, it looks even better, right? So it's doing something, it's working, that's what we want. Okay. Now, sharpening. Unfortunately, I could not get my hands on the PowerPoint that describes what sharpening is. But when we do find an element method, that depends on the advection equation. So what sharpening is that we take something and matrix, we kind of add and subtract it to the original equation. So in the strong sense, it's the same thing, but when we discretize, it's different, right? This kind of messes up mass loss sometimes. So this, I'm sorry, not mass loss. It messes up balance preservation, but it makes things look a lot better. It kind of gets rid of some of the nonsense out here. So that's what sharpening does. It helps us. So, and we also applied the FCT projection that I mentioned earlier. So this is how it looked with no sharpening term, right? So we applied FCT projection, so things look a little bit nicer. But one thing that I do want to point out, because these do look kind of similar, is the mass loss, right? Mass loss for mass average, about, again, on the scale of 10 to the -5, but then the mass loss here is even smaller, 10 to the -6. Again, that's what we want to see. But whenever we add the sharpening term, so whenever, I don't know about you guys, I can see a very clear difference here between the sharpening term and the non-sharpening terms here, right? There's not, we have this kind of green fluff out here on the mass average, and that's completely taken away over here for this mass average. And same thing with the log plots, it's even more obvious. So yeah, so sharpening improves things. But another interesting thing is that our mass loss is actually a little bit worse, right? So our mass loss is slightly better for the mass average, but whenever we do our LOR refinement, it's actually a little bit worse. So that's a little bit interesting. And I mean, that kind of makes sense though, right? Because we are changing the base equation. So we expect the mass to be, we're expecting the mass to change, right? Because it's an entirely different equation. Okay. So FCT blending, again, we're mashing the low order and the high order solution. We're mashing them and we're setting them off as a new solution. So what happens when we do that many times over, when we're just mashing solutions together and seeing how that affects it? We thought it'd be an interesting problem. So we applied it once, right? So this is kind of, whenever we were using FCT projection over here, this is what that was kind of the basis that we're working at. Standard result, FCT applying it twice. Not really much of a noticeable difference, not in my opinion, but the mass loss is getting bigger, or it's getting smaller, right? So, I'm sorry, it is getting bigger. But, so that's kind of interesting that as far as mass loss goes, it's actually getting worse, right? Which is weird because this FCT projection is a conservative and it's a projection operator, right? It should be conservative. Then when we apply FCT 3 times, yeah, it gets even worse. And it's a little bit hard to see, but if you look at the log plot, you can kind of see these little artifacts, these little doodads down here, right? That's not what we want to see, right? That shouldn't be there. But then I decided to kill it with fire with 10 iterations. And then you really see these little fellers out here, just kind of chilling. That's not what we want to see, right? But it is an interesting result because it's telling us something. We're learning from this. And again, our mass loss is getting bigger. That's not what we want. So just based off of this, it seems that only applying this FCT project once is the way to go. We had a bunch of guys telling us just apply it more, apply it more. It's probably going to help. It never helps. So we're not done here, right? All the tests that I showed you, we were kind of ignoring the bounce preservation thing because sharpness really ruins bounce preservation, right? Because we're literally changing the equation. So the bounce preservation isn't working as well. So how do we fix this? Well, the low order solutions depend on DT. It's probably not terribly obvious, but it's the details that explain that are a little too intricate for this talk. So for certain problems, having a larger DT is a problem. So what we decided to do is we decided to adaptively refine DT. So if we're in bounds, we're increasing DT. If we're out of bounds, decrease DT and repeat the solve. And again, we're going to apply FCT projection many times. What? Why does it look like this? Okay, well, these are time steps. I think this is because that we're not in PowerPoint. We're not in Microsoft PowerPoint. I think we're on the browser. That must be what it is. But anyway. So this first plot right here, this is for the mass average, right? So we're not doing LOR at all. This is old stuff, right? So here's how the DT's looking, right? Increasing by a factor of 1.02 looks pretty good. Then at around DT equals 0.02, kind of started to look bad. Bounds violations are happening, so we decrease it. Nothing super interesting there. Very standard results. This does not have sharpness, by the way. So, and then when we introduce LOR, it's almost the same result. So nothing terribly interesting here, just kind of standard stuff. Sharpness helps how everything looks, right? We already went over that. So how do we remedy this? Or how do we remedy sharpening and pruning things? Well, we're going to include sharpness in our adaptive refinement, right? Sharpness depends on a certain coefficient. The coefficient we want to be as high as possible, right? We normally stick with 1. The closer it is to 0, the closer it's getting to just a basic non-sharpening problem. So how does it look? We have the DT history and the sharpness coefficient history, right? So anytime, and we included an upper limit on this, right? Just so it's not exploding and just ruining everything. Now, again, DT not super interesting. It's kind of looking like it did before. But the sharpness coefficient I think is quite interesting, right? Because we want it to stay around 1, but it is not looking like it's around 1, right? It's dropping all of them, all the various types of all the number of times we apply FCT project is just dropping instantly to like 0.02, and then it's kind of coasting. And the most interesting thing here, I think, is that whenever we apply FCT iteration once, it's increasing to about 0.08 or 0.8, kind of staying there, going back down, going back up. So based off of this, we're getting the best sharpness results whenever we're only applying FCT iteration once. So we thought that was a pretty interesting result. Now, that didn't look very good, right? The sharpness was really low. We want to have the sharpness as high as possible. So we decided to say, all right, well, DT was equal to 0.005. Let's cut that down to 0.001. And this is the results that we got for the sharpness coefficient, right? So, oh, that looks so bad. I'm sorry about that. These are all time steps. This is taking about 1,000 iterations to converge. So kind of hard to like really discern anything, but I think one of the most important things to get out of this is that we have this red line right here. You see it's kind of consistently staying at about 1, dipping down a little bit, coming back up, and then kind of consistently staying at 1. Right. So that kind of tells us that if we want to maintain this sharpness, if we want to maintain the pretty pictures, then we need to have a small DT. There's no other way around. And if you're in computations, then you should know that with computations, there's no free lunch, right? You have to have some sort of sacrifice somewhere. And for this project, it seems that DT needs to be the one that, that bites the bullet here. So, and actually, interestingly enough, all these bounds preservation issues, whenever we have a bounds violation, it usually is only one element, which is really interesting, that it's just one element on the scale of 10 to the -8. Like it's just out of bounds just by that little. It's very interesting. You don't know why. That was kind of at the tail end of the internship that we didn't get to explore that really. But yeah, so applying FCT iteration once, that seems to be the way to go. And then kind of the final thing we did in the internship was obviously just do some optimization, because the way we had it coded in was just unacceptably long, right? So if I wanted to have 4 refinements on our solution, that's going to take about 2 minutes, whereas the base mass average would take about 20 seconds. That is unacceptable. So with the tutelage of the lovely Arturo, we were able to cut that down from about 140 seconds to about 50 seconds. So that was really nice, really satisfying. It was honestly probably one of my favorite parts of working on it. It was going through the code and cutting out certain computations, making sure things that aren't multiplying more times than they need to. So yeah, and after the optimization, it's more of a, well, got to cost us about 20 seconds to use, the mass average solution. But if we want a really clean solution, it's going to cost us about 2.5 times as much. So again, and you have options too, right? So to give a little conclusion here, we created a new low order method to solve things. It is bounds preserving. It is mostly mass conservative. It is more mass conservative than other low order methods, which is good. We successfully implemented in the rem host, and my mentor implemented in the blast, which was if you remember the big code that we're looking at. We investigated the sharpness. We investigated applying FCT project, usually fixed by adjusting DT. Yeah, that was it.
So the code, the Marbl, and the blast that you talked about at the beginning, is that something that's out in the real world, or is that a Livermore code?
That is a Livermore. You need to pass their super secret.
Gotcha.
Their super secret clearance. They get access.
I would
to that.
assume that people at Livermore sometimes publish papers, but I guess they have to go through censors, right?
Yeah. So, like Remhost and Mthem, what I worked on, that's all open source. You can see all that. You can see the work that I did on it, but not Marbl. Marbl absolutely does not beat the lab.
Okay.
It's actually an entirely different computer to work on. And I saw your hand go up.
So at the end of it all, you decided that just keeping a small delta T was the best move, because you were talking about possibly, when things weren't so sensitive, increasing delta T probably to speed up the computation was probably the idea. But you decided to the -2, right? Just to use a constant DT.
Well, it's not like it's not like I reported when people say this is the best thing to do.
Yeah.
It was more of like, here are the options we have. And if we really super duper want sharpness, then you kind of really need to cut DT down.
Okay.
If you ask me, I would just say get rid of sharpness entirely, because we really get the nice clean bounds preservations on that. Because that's really what we want, right? Like that's the whole point of the project. That's the whole point of having a low order solution. So does that answer your question? Yeah.
Other questions? All right, well, let's thank our speaker again. Thank you. Oh, yeah, that's a good idea. So thank